Here, if we look back at the waveforms, we have a signal here that has a 1 second duration, and it's 5 cycles per second signal. 1 cycle per second is called 1 hertz. So this would be a 5 hertz signal, 5 complete sine waves in 1 second's duration. If we increase the frequency slightly to 7 cycles per second, 7 hertz, we have a signal that is slightly higher in frequency. If we compare this with sound waves, sound has a higher pitch with the higher frequency. The lower the frequency, the lower the pitch. Another property is wavelength that we can measure at the same point between two successive waves. So if we go from the 0 reading on the up curve here to 0 reading on the next up curve, that's the wavelength. Or if we go from peak to peak or trough to trough, the wavelength will be consistent for the same analog signal. These are typically called analog signals, very different from digital signal processing. Now we can also look at amplitude. In an electrical signal, an amplitude represents voltage, and the higher the potential difference, the higher the amplitude. Here's a 2 volt high signal, and then 3 volts is 50% higher, 4 volts is 50% higher yet, 6 volts even higher. So the amplitude of the signal indicates the strength of that voltage signal. Also in the sound wave case, the higher the amplitude, the louder the sound. So both sound waves and electrical alternating current produce identical looking waveforms. And so we'll be studying both of these waveforms when we look further at the electromagnetic fields and look at the electromagnetic spectrum, which is where all of the wireless communication happens in our electromagnetic spectrum. And so we'll need to be aware of these properties of frequency and wavelength. As the frequency increases, the wavelength is decreasing. And so the shorter the wavelength, the higher the frequency. And that contrasts greatly with direct current or DC current, which is always going to be shown as a flat line on a voltmeter. So if we were to look at our DC type current, we have a voltage level. We go up to some peak plus or minus voltage level, and that voltage source would be completely flat. So this will make it a bit easier to talk about DC circuits, which we'll look at schematics for, like our previous circuit that we looked at here when we had the metal filings around the electrical current. Shown coming up right here. So this is a simple DC circuit. A direct current means a battery as its source, and this will have very simple electrical properties. And this is how the first telephones worked as well. They were DC powered devices. They had to be battery powered devices, and getting the power to the phone was one of the first technical challenges. The early phones had to come with a large wet cell battery in order to provide the power. Here we show the two different types of electrical power. Alternating current is on the top, and that's given by this characteristic sinusoidal waveform shape of the voltage. And direct current or DC current, which is shown at the bottom, which is given by the characteristic flatline constant level of voltage. Now, depending upon the source of the voltage, we might see a potential difference here between the highest voltage here is reading 0 and the lowest minus 48 volts. The current is directional, and the difference in potential here is 48 volts. This could also be expressed as a plus 24 volts on the top end and a minus 24 volts on the bottom end in talking about voltage. The plus and minus signs just relate to the direction of the magnetic field of the electrical force. So to review, electromagnetism is the combination of both electricity and magnetism that are coincidental in the same circuit. Simple bar magnets can generate magnetic fields. Dissimilar poles attract one another with an attractive magnetic field, and similar poles repel one another. A simple bar magnet can be made into a horseshoe magnet, and we can exploit this property by creating a directional magnetic field, and we can get the two magnetic fields interacting with one another in either an attractive way when the opposite poles are facing one another, or in a repelling kind of manner when like poles face one another. And in fact, we can do this in combination between attracting and repelling. Attracting is like pulling forces together, and repelling is like pushing forces. And if we want to, in effect, move some kind of object, we could use both of these forces at once. We could be pulling on one end and pushing on the other. And some of the high-speed trains use this magnetic property. Very strong electromagnets generate the magnetic fields that have this directional property, so that it's being pushed from behind and pulled from the front to generate the high speeds. We can exploit these magnetic fields in matter, in actual physical particles like copper. Copper is an electric conductor. It's an excellent conductor of electricity because of its atomic makeup. Being atomic number 29, it has one outer electron in its valence shell, the outermost shell. It's the greatest distance from the nucleus, and so the nucleus is populated with protons and neutrons, so the nucleus is very heavily positively magnetic, and the positive nucleus with the negative electrons keep these electrons in orbit. The closer electrons are in a more powerful magnetic field than the next level out. So as we go out to outer shells, the force by which these electrons are being held in orbit is getting lesser and lesser. And so this electron out at the outermost shell is most easily given up by the copper atom. And in fact, when we have a copper wire, we have a dense clustering of these types of atoms. And if we can induce a current on one end, a negative current would repel these negative particles. They would be pushed away, pushed through the copper wire. And likewise, if we had a positive force on the opposite end of the negative end, that would be a pulling force. And so we can pull a flow of electrons through the copper wire back to the device. Such is the state of a DC circuit like this one right here. This would be the negative end of the battery at the top, and the positive end would be at the bottom. The negative end is pushing the electrons clockwise around this loop, and the positive end is attracting them. Now, given the makeup of the battery can produce this source of electrons, and as the battery ages, the difference in voltage between its negative terminal and positive terminal will get weaker and weaker with time. The battery would be in effect wearing out. But as the battery is generating this electrical current, if we were to take a hole in a sheet of paper here and then push the wire straight up through that, holding the sheet of paper flat, we could dust some metal filings on the paper, and we would notice that with the stronger the electrical current, the larger the potential difference, the larger the voltage difference in this circuit, the more we'll see those metal filings form rings, concentric rings on the sheet of paper. That's the result of the magnetic field being induced by the electrical current. The left-hand rule captures this phenomenon. Using your left hand, your thumb indicates the direction of the current in the wire, and your fingers indicate the direction of the magnetic field generated by that current. So whenever we have electrical flow, we also have a magnetic field. Likewise, with a generator, we have just the opposite. We can take a magnetic field and move the magnetic field and generate an electrical current, a voltage difference. The best analogy in the physical world would be to drums of water shown in this plumbing type setup here. Flow of water through the pipe is controlled by this valve. The valve would operate like a switch in an electrical circuit. When we close the switch, we are completing the circuit, and then the electrical flow can go completely through the circuit. The resistance in this diagram here is given by the diameter of the pipe. The greater the diameter, the greater the flow of water, the slower the force in emptying the left drum into the right. By increasing the diameter of that pipe, we would actually be increasing the flow. So the flow of water is like the flow of electrons, electricity in a circuit.